Good morning, class.
Hi, Hazel.
Hello. I will wait about one more minute and then I'll get started. We got doggo action happening here. We got doggo action. We got butt sniffing happening. Bug, don't do that. Don't do that, Bug. Always got a taste in. Bug's got a taste in. Sometimes he smells something funny and then he'll start going. So he just sniffed Hazel's butt and started going. All right. So today, I don't really have, so this should be a fairly quick lesson. Really what I'm going to do is I'm going to introduce today's assignment. And we're going to continue to use the Apache Commons Math API. So let's see. So basically what this assignment is, it's called Disease Spreader. And the purpose is to model the spread of a disease throughout a community. Okay. So what I want to start off with is I want to remind you about the differential equation for the first differential equation we talked about, which was dy dt equals a constant times y. All right. So this is called the rate of change. All right. Rate of change of y. And so in this case, y is equal to, for this assignment, it's y is going to be number of people with disease. Okay. And then t is time, maybe in days, let's say. And then c is a growth constant. Okay. So if you were to solve this differential equation with the Apache Commons Math API, what you would find is, and by the way, in order to solve this equation, you need the initial condition. Okay, so how many people? So basically, that is what is the number of people with the disease at time 0? Okay, so how many people start? And so this equation is the equation for exponential growth. Okay, so if we were to graph y as a function of time, it starts out at the value y0, okay, and as time goes on, it grows exponentially, okay. Now, the growth constant determines how rapidly it grows. All right, so if you have a bigger growth constant, it's going to curl up faster. Okay. If you have a smaller growth constant, it's going to curl up more slowly. All right, so this is big growth constant. This is small growth constant. All right, so it's exponential growth. And if you started out with fewer people with the disease, so then that means that the graph starts out lower. Okay, so this number right here determines where it starts along the vertical axis, and then the growth constant determines how quickly it grows. So yeah. So now, what if we had? So what I'm trying to model here is a number of different countries. Okay. So what if I had some countries, and let's say that I had a world with 4 countries in it. All right. So we have, and because this is computer science, we're going to start out our countries with 0. So we have country 0, we have country 1, we have country 2, and we have country 3. All right. Now, because each of these countries, so these are countries. All right. And then y sub I is equal to the number of people with the disease in country I. And then each country is going to have its own growth constant. Okay. So as we have seen during the COVID pandemic, there are different different policies that have either enhanced the spread of COVID or reduced the spread of COVID. So these policies are essentially what are setting the growth constants in these individual locations, whether it's a state or a country or whatever. The one that comes to mind immediately is New Zealand, right? New Zealand had really strict lockdown policies, which made the growth constant for New Zealand for COVID extremely low. Okay. So let's say that country 0 has a growth constant of let's say 0.1. Country 1 has a growth constant of 0.05. Country 2 has a growth constant of 0.08. And then country 3 has a growth constant of 0. Let's say 0.2. So basically, country 3 has the highest growth constant, so that would represent the country with the most relaxed policies. Okay. So if these countries are just completely separated from each other, which, as we know, that's not the case. It's global. Okay. Okay. So if the countries are completely separated, then what we would have, is dy0 dt. So the rate of growth of country 0's disease is going to be 0.1 y0. Okay. And then the rate of growth of country 1's disease with respect to time is going to be 0.05 times y1. Okay. And then the rate of growth of country 2's disease with respect to time is going to be 0.08 times y2. And then the rate of growth of country 3's disease with respect to time is going to be 0.2 y3. All right? So that is if each country, okay, is completely separated from every other country. But we know that that's not the case. All right? People travel between countries. Okay? But the interesting thing is there are different frequencies of travel between countries. Okay? So for example, in the United States, we're probably more likely to travel to Mexico or to Canada than we are to travel to Russia. I mean, I don't know for sure, but there's different links between each country. Okay, so we're going to model that the amount of connection between countries as a link in this. Okay, so we'll say that country 0 is connected to country 1. We're going to say country 0 is connected to country 2. All right, we're going to say that country 2 is connected to country 1. We're going to say that country 2 is connected to country 3. All right, and country 2 is the only country that's connected to country 3. So maybe, this is Russia and then country 3 is North Korea or something like that. I don't know. All right. So is country 0 connected to country 3? Yes, just not directly. Okay, because what could happen, how could COVID or a disease get into country 3? Well, it could get into country 0, and then country 0 transmits it to country 2, and country 2 transmits it to country 3. Okay? So what we then want to do is we want to describe the strength of the link. Okay? So maybe country 2 and country 3 have a really strong link. Okay, so we're going to say that they're So we just have to come up with a number that represents the size of the link. And I'm just completely making these up because this is a pretend world. Okay, so maybe this country 2 and 3 have a link of 0.5, of strength 0.5. All right, maybe country 0 and country 1 are incredibly strongly connected with each other. Okay, so maybe this is 0.9 is the size of their link. Okay, country 1 and country 2 are hardly connected to each other at all, so maybe their link is 0.1. Okay, and then the link between these two we'll say is also pretty small, so maybe 0.2. All right, so we're going to let L sub ik equal the link size between country I and country K. All right. So, and anyways, the link is going to mean that even if a country doesn't have any COVID cases, right? If you start out with 0 COVID cases, you're never going to have any 0 COVID cases. But because of the link, another country can bring COVID in, okay? So what we do is each country has its own growth constant, but then its rate of growth of the disease is affected by its own amount of the disease, but then it's also affected by the amount in the other countries, okay? So country 0 is linked to country 1 with strength 0.9. So I'm going to add plus 0.9 y1. Okay. Country 0 is linked to country 2 with a strength of 0.2. So then I'm going to have plus 0.2 y2. And it's not connected to country 3 because there's no direct link between them. All right. So this is the equation for the growth of country 0. Okay. So it depends not only on the amount of cases in the country itself, but also on the amount of cases in countries that it has a connection with. Okay. So let's do this one. Okay, okay. So country 2 is connected to country 0 with a link of strength 0.2. Country 2 is connected to country 1 with a strength of 0.1. And then country 2 is connected to country 3 with a link of strength 0.5. Okay. So that's the growth equation for country 2. All right. And then for country 1 is connected to country 0 and to country 2. So the link with country 0 is 0.9. The link with country 2 is of size 0.1. And then lastly, we have country 3, which is only connected to country 2, but it has a strong connection with it. Okay? So, there you have it. And so then what we would have to do, so you might remember that when we were talking about the Apache Commons Math differential equation solver, you have to have the get dimension of the problem. So basically there are 4 countries. So in this case, get dimension returns 4 because there are 4 countries. Okay. And then furthermore, our initial conditions well, there's going to be 4 initial conditions for the initial conditions of each country. All right. So, you have y0 at time 0. You have the amount that country 1 has at time 0, the amount that country 2 has at time 0, and the amount that country 3 has at time 0. Okay? So, maybe country 0, country 1, and country 2 don't start out with the disease at all. Okay? But maybe country 3 starts out with 5 cases. I don't know. What's going to happen is that country 3 has 5 cases, all right? So we can see that country 2, country 0, and country 1 won't make the number of cases in country 2 grow, okay? But country 3 has some cases. So that's going to cause country 2's case rate to grow, all right? Now, once country 2 has cases, it's going to transmit to country 0 and to country 1, but mostly to country 0 because the link is stronger. Okay. And then country 0 is, and country 1 is going to start getting the disease from both country 2 and country 0. So we can model the spread of a disease throughout the population. Okay. And these are kind of the most realistic initial conditions because, a disease starts in one location, right? It would be extremely unlikely for a disease the same disease to originate in 2 different places simultaneously, right? So it's always going to be a situation where, no one has it except for one place, and then it spreads out of that place. And then the directions that it spreads in depends on the links between different populations, okay? So if I were to write the growth equation abstractly, so the rate of growth of country I's amount of disease is going to be the growth constant for country I times the amount of the disease that country I has plus the links, all the links to all the other countries. So Li sub k, y sub k. And then we want to sum over all of the countries that it links to. Okay, so this represents these other terms, like for example, these 3 terms. We're summing over all of the countries that link to I. All right. So what you're going to do is you are going to model. I think I have a world with 5 countries for you guys that you are going to model. And you're going to see how long it takes for a certain country to achieve a certain case level. Okay? So I hope that I've described the assignment, and I hope you find this interesting. So this is a type of problem that is, actually with this problem, you could solve it by hand. It would just be really, really, really laborious, okay? So computers are really good at modeling complex systems and crunching the numbers in a way that is a lot less painful to humans. All right? So that's my lesson for today, and I will see you in the Zoom room. Okay?